In this video, we will work through an exercise from Introduction to Analysis. This is exercise 2 from chapter 2 on page 79, and we're given a function, f of x, and asked to prove that f has a limit at -2 and find it. So we'll do those two things in reverse. First, we'll find it, we'll find out what the limit is, and then we'll prove it. So to begin, let's look at the function that we're given, and let's try to simplify it. It looks like that numerator might factor 2x squared plus 3x minus 2, and it does. That factors as 2x minus 1 times x plus 2. And then notice that x plus 2, which is a factor of the numerator, is the denominator. So if x equals -2, we get a 0 in the denominator, but otherwise, this function simplifies. The x plus 2's cancel out, and it simplifies to 2x minus 1. Also notice the domain of our function. I'll call this D for domain. The domain is the open interval from -2 to 0. So in this interval, x is never -2. And so for that reason, on the domain, f of x always simplifies to 2x minus 1. So that's a much simpler way of writing the function as opposed to the way it was given. Now the limit as x approaches -2 of f of x. To find this limit, we could see what happens to 2x minus 1. And there, we could just plug -2 in for x and get -4 minus 1. This is -5. So it looks like the limit as x approaches -2 of this function f of x is -5. Now let's prove that. And to prove it, let's look at the definition of what it means to be a limit of a function. This is from the same book, Introduction to Analysis, the definition of what it means to be a limit of a function. So the first sentence here is let f from D to R, D for domain, R for range, let f from D to R with x sub 0 and an accumulation point of D. So let f be a function. Okay, so let's see what they're saying here. So D in our problem is the interval from -2 to 0. X sub 0, we're taking the limit as x approaches -2. That's x sub 0. And that is an accumulation point of D. Since D is an open interval from -2 to 0, the accumulation points for an interval are all the points in the interval, but it also includes the endpoints. The definition of an accumulation point of a set is so the reason -2 is an accumulation point is we can find a sequence of numbers in our set D that converges to -2. That's the definition of a accumulation point. So the first sentence is satisfied in our exercise. And this first sentence is really technicality. It's not something we're going to have to worry about in any problem. If x sub 0 were not an accumulation point, we couldn't define the limit. So if we say, let's find the limit as x gets closer and closer to x sub 0 needs to be in our domain of our function, or it needs to be close to the domain of our function. Otherwise, this definition wouldn't make sense. The main point of this definition is the next sentence. Then f has a limit, L at x sub 0. So this is going to tell us the definition of what we want. And L, for us, the limit, we're saying that's -5. So the function f has limit -5 at -2 if and only if for each epsilon greater than 0, there is a delta greater than 0. So I'll stop there. It says, given any epsilon bigger than 0, the definition says we should be able to find some delta bigger than 0, so that if this is true, then this is true. It's an if-then. So our goal is to find, given epsilon greater than 0, our goal is to find delta, but we have this condition. I'll write it down. If 0 is less than, but I'm going to substitute in. This is x minus -2. X sub 0 is -2. If this is true and x is in D, then the absolute value of f of x minus L is less than epsilon. So that's what we want. We want to find delta that makes this true. And so what we can do here is let's just look at what we want here and see what that says about delta. So this is not going to be the proof, because in a proof we should not assume the thing we want to prove. I want to prove this is true. This is the then part. But for now, let's assume this. And let's look at what this says. I'm going to substitute in f of x on our domain D. F of x was 2x minus 1. Minus L was -5, so that's minus a -5. This says 2x minus 1 plus 5 is less than epsilon. And I'm going to simplify that. 2x minus 1 plus 5, 2x plus 4 is less than epsilon. That's what I want. I want 2x plus 4 to be less than epsilon in absolute value. And my question is, I want to know what I should let delta be to make that happen. And the key thing about delta is our condition is that we know the absolute value of x plus 2 is required to be less than delta. So I want to look to see, where is this x plus 2 in our problem? I don't see it yet, but if I factor out a 2, I get exactly that, x plus 2. So this is what I want. I want the absolute value of x plus 2 to be less than epsilon over 2, dividing each side by 2. That's what we want. And we want to find a delta that makes this happen. Well, x plus 2, the absolute value of x plus 2 is less than delta. And we want the absolute value of x plus 2 to be less than epsilon over half. So just putting these two things together, we can let delta be epsilon over 2, and this should work out. If I'm assuming in my if part that the absolute value of x plus 2 is less than delta, then when I get down to here, the thing that I want is less than epsilon over half. Well, that's delta. That will work out. So we just figured out a good value of delta that will do what we want. And again, this is not the proof, because to find this, I was assuming the thing I want to prove, which we shouldn't do. Now I'm going to go up and write the proof. And when I write the proof, I'm not going to assume what I want to prove. This is really going to be the same work we just did, but reordered a bit. So in our proof, I'm going to look at the definition. And the definition, it says, for any epsilon bigger than delta, for any epsilon bigger than 0, there exists a delta bigger than 0, so that something is true. So I'm going to start by saying, given epsilon bigger than 0, and I'm just going to say what delta should be. Let delta be epsilon over 2. And I'm going to prove that this works. And what it means to work is, if this if part's true, then the then part's true also. So I'm going to assume the if part. Assume 0 is less than x minus x sub 0 is what's in the definition. But I'm going to assume that x minus -2 is less than delta for x in the domain. And I want to show that this is true. I want to show the then part. I want to show that the absolute value of x minus L is less than epsilon. So I'm going to pretty much do what I did before, but I'm not going to assume it's less than epsilon. I'm going to show it's less than epsilon. So assuming all of this, let's look at the absolute value of f of x minus L. Let's look at this and see what this equals. Well, for starters, I can substitute and say this is 2x minus 1. L was -5, so minus L is plus 5. And then I can simplify that. That equals the absolute value of 2x plus 4. And now I can factor out the 2. And if I want to use the distributive property, I can factor using the distributive property, but then I can use the fact that 2 is positive to get that outside of the absolute value. This is 2 times the absolute value of x plus 2. But now I'm going to scroll up. I'm assuming, in the beginning of my proof, I'm assuming that this absolute value is less than delta. So this So 2 times this absolute value is less than 2 times delta. I'm also assuming I define delta to be epsilon over 2. This is 2 times epsilon over 2, and the 2's cancel. This is epsilon. So by this string of equalities and inequalities, I started with the left side of what I wanted to show, the absolute value of f of x minus L, and I show that that is less than epsilon. So by putting this all together, assuming that the absolute value of x plus 2 was less than delta, I proved that the absolute value of f of x minus L is less than epsilon. That's exactly what we want to do in this definition. So assuming the if part, I prove the then part. And again, the key part of the proof, what makes it a proof, is I'm not assuming the thing I want to prove. I'm only assuming the premise, which is that epsilon's greater than 0. I'm assuming the if part involving delta, and then I'm proving the then part involving epsilon. So we could put this together into a proof. Now, this is still not a finalized proof. This is a rough draft of a proof. I'd want to write this out more cleanly, maybe type it up, and also give a reason for each step. And also a concluding sentence saying, therefore, we have shown what we want to show, and the limit of this function is -5 as x goes to -2 by that definition.